First of all, thank you for the INQA organization for holding a conference, and I'm honored to present my work here. I'm Shunta, actually undergraduate student from Keio University, Japan. Today, I'm going to talk about our proposed new variable deduction method for the constraint combinatorial optimization problem called the multi-penalty sample percent variable deduction. The presentation is based on the preprint we have recently uploaded, so if you're interested in, please scan QR code. Here's the agenda of the talk. Let me go through the motivation of our research. The combinatorial optimization problem is a problem to find a combination of discrete variables that minimize the objective function within the given constraint. And such COPs are difficult to solve due to the exponential growth of the solution space, and against this difficulty, Ising machine are promising solver. To solve COP with Ising machine, the problem must be formulated as a Kubo form, quadratic unconstrained binary optimization form. COPs in the real world often have constraint, and which is called constrained combinatorial optimization problem, CCOPs. To incorporate such constraint into the Kubo framework, unconstrained framework, the typical formulation is with penalty function method. According to it, the objective function is written as the original summation of the original function and the penalty function weighted with penalty coefficient mu. The penalty function takes positive value when the decision variable violates the constraint, while 0 if constraints are satisfied. Here's the main challenges when solving the combinatorial optimization problem with Ising machines. As I said in the previous slide, the COP in the real world often have a constraint, and the number of decision variables tend to be large. So it's important to solve such large-scale CCOPs. First, the hardware limitation, the number of variables or a coefficient, and the magnitude of the coefficient are limited. Also, the graph structure of the original, especially in the quantum learning machine, the graph structure of the physical qubits are unique, called such Pegasus graph or Chimera graph. Which necessitating the additional physical qubit to represent our single logical decision variable. The second, solution degradation. It has been shown that therefore the solution degrade as the number of decision variable increase. Also, the third one, the adjustment to the penalty coefficient. As I said in the previous slide, the penalty coefficient must be large enough so that the ground state corresponds to the feasible solution. However, too large penalty coefficient overemphasize the penalty function, which leads to the solution degradation of the original objective function as well. And against the hardware limitation and the solution degradation for larger scale problems, the variable deduction is one of the most effective methods. The variable deduction is the algorithm to simplify optimization problem by identifying a fixed variable whose value likely determined to mitigate the hardware limitations or to obtain better feasible solutions. Here's the example of the variable deduction, and the mini variable deduction has been proposed. And I want to emphasize here is that the variable deduction is not only for the Ising machine, but for any type of the general combinatorial optimization solvers. The basic idea of the variable deduction is basically common across multiple algorithms. Is that finding a persistent variable. I mean, the persistent is the variable tendency to take the same value across the multiple solutions. The way to determine such such a persistent variable differentiates algorithms such as the correlation function, utilizing a correlation function between two spins or expectation value or one single spin free energy difference and so on. And in quantum ring, variable deduction also has been shown to expand the energy gap between the ground state and the first excited state, and improve its performance as well. Let me explain the variable deduction method in more detail using the sample processing variable deduction, SPVAR, as an example. This method is also serves as the foundation of our proposed method. The SPVAR algorithm is a variable deduction method to variable deduction algorithms that usually has hundreds or thousands of solutions obtained from a quantum annealing machine. Due to the short turnaround time, it is easy to obtain hundreds or thousands of solutions from a quantum annealing machine. And returning such solutions, the variables that tend to take the particular value are fixed to the value. Let me explain with this example. The original problem was solved. The three solutions are obtained. The number of solutions could be larger, but for simplicity, only 3 solutions. And the variable x4 takes 1 across all the solutions, so consider to take 1 in optimal solution, so fixed to 1. And x2 takes 0 for all the solutions, so fixed to 0. And as a variable, treated as variable, and by solving the reduced problem, the final solution obtained. The SPVAR algorithm has been applied to these benchmark problems and has been shown to improve success metrics such as the probability of obtaining optimal solutions. So here I've introduced such promising variable deduction method. However, they also of course have the limitation. COP in the real world, I said at the beginning, COP in the real world often have a constraint and also have a large number of rotation variables, so CCOP, basically CCOPs. So, however, a few CCOPs are benchmarked with a variable deduction method, and a few CCOP are actually benchmarked with, but with a fixed penalty coefficient. So when solving CCOP with any of the previous method, you have to find the penalty coefficient considered appropriate before applying a variable deduction method. In practice, appropriate penalty coefficient is often determined experimentally. So you will evaluate the optimality and feasibility by setting the multiple penalty coefficient. From this observation, it's quite natural to ask what would happen if we fix the variable based on the multiple solution obtained on the different penalty coefficient. So that's our purpose. Again, propose a new variable deduction method that utilize the multiple solution information obtained at different penalty coefficient. And this method has been this method is expected to produce a high quality and also feasible solution. Then it's our proposed variable deduction method called multi-penalty sample processing variable deduction, the extension of the sample processing variable deduction. This is the variable deduction method for CCOP, utilizing the solution information obtained on the different penalty coefficient. And the same as the SPVAR, the variable that often takes the same value across those solutions and fixed to the value. Also, let me explain with this example. First, we choose a penalty coefficient candidate, n mu penalty coefficient candidate from mu1 to mu n mu. And for each penalty coefficient, NP solutions are obtained. So in total, m mu times NP solutions are obtained. And using this solution information, the variable often take 1, fixed to 1. And 0 to 0. Within the parameter setting, we use the variable that that take the same value across all the solutions fixed to the value. So as shown in this example, right, only the variable that takes the same value. The strictest fixing threshold. Also, the mu sub, which is the penalty coefficient set to the reducer problem, is set to the penalty coefficient, which yielded the best feasible solution within the penalty coefficient candidates. To evaluate our proposed our method, we conducted a numerical experiment on the benchmark problem called the quadratic assignment problem, a QAP. The QAP is a problem to assign a facility to a location while minimizing assignment cost. QAP is a mathematical problem, but it also appears in the many real-world situations for such as layouting problem or assigning problem, and so on. And here is the Kubo formulation of the QAP. The DRJ is the distance between location I and location J. FKL is a flow from facility K to facility L. XIK is a binary addition variable that takes 1 if and only if facility K is assigned to location L, otherwise 0. And mu is the penalty coefficient, and the constraint ensures that only each facility is assigned to only one single location. Here's the more detail of the experimental setting. The benchmark problem is a TAI-60V from QAP list. The benchmark or library benchmark problem set for the QAP. And TAI-60V is the 60 facility QAP problem. So the number of addition variable are 3,600. And as Ising machine, we employed the Fixstars Amplify Annealing Engine, which is a simulated annealing GPU-based Ising machine. And the timeout, which is the parameter to specify the calculation time, was set to 5 seconds. And the performance metrics, we use the standard metrics such as approximation ratio and the feasible solution ratio. And here is the result when changing NP from 1 to 10 for all combination of penalty coefficients 0.1 and 1, 10, 100. We consider that this choice of the penalty coefficient cover a wide variety of a wide range of values because we normalize this DRG and FKL. And the NP, NP is the number of solutions for each penalty coefficient. And the above 4 rows here is the original SPVAR method with only one penalty coefficient. And the penalty coefficient mu equal 10 and 100 produce a feasible solution with probability 1. And in the case of the MPSPVAR as a low, except for this above 4 line, only the 0.1 and 1 produce no feasible solution. So MPSPVAR produce a feasible solution when the combination of penalty coefficient include at least one penalty coefficient that produce a feasible solution. This behavior was discussed based on the analysis of low energy state and a small large penalty coefficient in our preprint. Also, here is the result of the average approximation ratio with MPSPVAR. Basically, the approximation ratio become better as the NP increase. The smaller is better. So as the NP increase, the approximation ratio get better. And the combinations that include more penalty coefficient that produce a feasible solution show the better performance. For example, 10 and 100 both produced the feasible solution in the naive method. Shows the better performance than other combinations. Also, these are the better performance because 10 and 100 produce the feasible solution. And also, the penalty coefficient that do not produce feasible solution contributed also slightly to the performance improvement. For example, the 0.1 to 10. 0.1 and 1 do not produce a feasible solution. However, comparing this, the top 1 and this 10, the approximation ratio is slightly better than the normal SPVAR method. So we also conducted the same numerical experiment on other QAP instances with different number of addition variables, and also observed the same trend. And moreover, we also benchmarked the MPSPVAR method on QKP instances, quadratic knapsack programs, The QKP is a CCOP with an linear inequality constraint. Basically, the constraint that can be handled within the Kubo formulation is a linear equality constraint and linear inequality constraint. The QAP is the CCOP with linear equality constraint. So, but QKP is linear CCOP with a linear inequality constraint. So. And also, the solution structure of the QKP is different from the QAP. So we also benchmarked the MPSPVAR on the QKP instances. The slight difference are observed also, but the same trend, basically the same trend was also observed. Okay, I conclude. Here's a summary of the talk. Again, the CCOPs in the real world often have a constraint and a large number of different variables. So solving the large-scale CCOPs is important. And when solving such a problem with Ising machine, here's the main challenges: hardware limitations or solution degradation for larger-scale problems, and penalty coefficient adjustment. And against these challenges, we propose a new variable reduction method called the multi-penalty sample percent variable reduction, which is a new variable reduction method to utilize multiple solution information obtained on a different penalty coefficient. Throughout the numerical experiment on benchmark programs such as QAP and QKP, MPSPVAR produced a better feasible solution than SPVAR. Thank you.
All right. Any questions? No, be fast. You're closer. So in the problems that you investigated, you only had one constraint, or didn't you also had multiple? I now don't quite remember.
In the QAP, only one constraint.
So how, if you have multiple constraints and thus multiple like parameters that you would need to optimize, how would you think that this? Well, because maybe you then need to like vary those parameters a lot more. I don't know if you have.
Yes, we only investigated only the case that the problem is a single constraint. However, it's possible to consider the, changing the parameter in another axis, like this is only for the mu1 from only mu, but for the another penalty coefficient, changing such another parameter and utilizing all the solution information and the variable fixing method that utilizing the other all the solution information is also possible, I think.
Thanks.
Thank you.
Thank you. So this method can be applied also for different kind of annealing schedules, right? So it's independent of whether you're applying simulated annealing, quantum annealing, reverse annealing, whatever. Yes. Just a way of reducing variables.
Yes.
Okay. I didn't understand, so in order to gain the statistics that you use to reduce variables, you need to be able to run the experiment. So that means that you're already able to embed the problem on the hardware. So it's a matter of improving the quality of results.
Yeah, basically, yes. So you mean to sample this solution to fixed variables, we have to solve the problem directly.
Exactly.
So, yeah.
Yes.
Yeah, that's the point, and I think the Ising machine to solve the reducer problem can be different from the samplers. I mean, the samplers could be the Ising machine that is capable of the large number of different variables, and the Ising machine for the reducer problem can produce such better solution.
Okay, clear. Thank you.
Thank you.
Okay. Any more questions?
Sorry, I had a question actually about the device that you were running this on, like this Ising machine from Fixstars.
Yes.
Is it like what type of device is that? Is it like a coherent Ising machine?
Actually, the internal algorithm of the Fixstars Amplify is not revealed.
Sorry, it's what?
It's not revealed. The
Oh,
internal algorithm is, they said the internal algorithm is based on the simulated annealing, but the complete algorithm is not, not revealed.
Okay, interesting. That explains why I didn't find anything on it.
Any more questions? Okay, then let's thank our speaker again.
Thank you.